that's kind of cool. And let's count this one up. T sub 4, 4, 3, 2, 1. What's 4 plus 3 plus 2 plus 1? Plus 3 is 7, right? 3, 7 plus 2 is 9. 1 more is 10. So who asked for multiples of 3? Turns out no. Hadn't thought about it. And of course this would be T sub 5. So let's figure out how many there are in T sub 5. Well, I've got 5 here. Plus 4 is 9. Plus 3 is 14, 15. Right? So notice my counting technique. I'm just counting 5 here, then 4, then 3. What was the number again?
Or we could just
if we go the other way. 1, then 2. Oh, well done. What was the number? 15?
Yeah, 15.
Okay.
10 plus 5.
See, this is a good group, right? So what you want? Right, we've got these triangular numbers, 1, then 3, then 6, then 10, then 15. And presumably there's a pattern, right, based in part on the way I'm counting them. The first one, plus 2 in the second row, plus 3 in the third if we go right back to the left.
That's good, actually.
Preparation.
I think the previous one and add the next.
Anyway.
Yes.
Just start again, John.
Yeah, let's just hit rewind.
All right, so what you want to observe here is that the nth triangular number, right, an arbitrarily large one, could be found by summing all of those natural numbers less than or equal to n. And of course, this I think is probably the easiest one. How do we get 15? 1 plus 2 plus 3 plus 4 plus 5. Right? So T sub 40 is going to be 1 plus 2 plus 3 plus 4, so on and so forth, plus 40. We're good? Kind of cool numbers. As it turns out, you can generate the triangular numbers using a formula. And we'll put this up on the board. And this is where these sit on the overhead. So what we've got here is a statement to be proven. N has to equal n parent n plus 1 over 2. So we're going to prove this using induction. Notice that it's indexed on the natural numbers, right? We could have 2, 3, 20, 60, 74, so on and so forth. We can have any whole number we want as our starting point for the triangular numbers. So there you go. That's statement to be proven. Is there anything else on this overhead? There we go. Now, let's talk about the first domino here. All right, so there you go. For every natural number n, the sum 1 through n simplifies to or can be generated by this form n plus 1 over 2. We need an anchor step or a base case. So what's the smallest value of n? What was the smallest triangular number? 1. So should be easy enough in this room. You guys all believe that? And what I do?
What did you do?
Yeah, what did we do?
You substituted the one for n.
That's it. All right, we took the smallest value that would make sense here for n, 1, first triangular number, and we checked the darn formula. Put a big check next to that. It's an important step. Why?
First goes along.
Because we've got to push the first one. Right? That's what we just pushed the first domino here. Boom. That's kind of cool. Now here, we didn't leave it up. Oh, we've got that. Let's just see what I wrote next. All right, base case in this example, smallest value would be 1. As such, we substitute 1, right? And we show that it's a true statement. Now we get to the inductive step. And this sort of has 2 parts, right? What we need to show is that if the kth statement is true, the k plus first statement must be true from the kth statement. So we'll assume that the statement is true when n is equal to k. That's called an inductive hypothesis. So here's our We'll put it down here for this. Right, and we are going to assume that this statement is true when n equals k. So what would that look like on the page? Tom, what do we do when n equals 1? We just subbed it in. So what do you suppose we're going to do with a k?
Put k where n
We'll just sub it in where n is. So we are assuming 1 plus 2 plus 3 plus. Boom. So that's a true statement as far as we're concerned right now. Easy enough? Okay. That's called a hypothesis. Now what we need to do is use that hypothesis, right, the inductive hypothesis, to show that the k plus 1 statement has to be true. So the question is, what would the k plus first statement be? What do we do with 1? We subbed it in for n. What do we do with k? Subbed it in for n. So what do you suppose we're going to do with k plus 1? It's a good group. Better than I expected today. So let's write that out. And let's just highlight it. Right, that would be the sum of the first k plus 1. Now, what would our formula n plus 1 over 2 look like when we sub in k plus 1? Right? Agree that's what it would look like? So k plus 1 in wherever we had an n on the right-hand side. Now, the standard technique that we use now, pick a side. Which side do you want to work with? Good. Good. That's the side we want to work with. We're going to take the left-hand side. We're going to screw around with it until we make it look exactly like the right-hand side. Once we've done so, what have we shown? What have we shown?
The k works for
That
all
the
values.
k statement forces the next one to fall. So let's play around with the left-hand side. Let's do that back here. That'll be pretty awesome. Awesome. That's going to have to go. Now we'll see if we can
That's
see it.
perfect.
You got that in there?
Gotta get squishy squished.
So we've got 1 plus 2 plus 3, dot, 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 plus k plus 1. So we're going to manipulate this statement now. So, quick question. If you examine your inductive hypothesis, what can I do with that?
K times k plus 1.
We could replace the underlined part, right, pink underlined, with k parent k plus 1 over 2. So let's do that here. We have k. Easy enough. So, any ideas? Common denominator. Common denominator would be? So, how would we do that? Let's see. That should work. All right, let's see what we got. This is where I depart from my notes. We'll see if it works. K. Agreed? Combine the fractions, pretty straightforward. What's in common on the numerator?
The common factor is k plus 1.
Common factor is k plus 1. Right, so what do you do with common factors?
The F word.
Factor?
Oh, I think it more in terms of I undistributed. Same idea, factor. Word, that's clever. All right, so bottom line. Common factor, pull it up. So what does that give us?